Today, lesson 27B. We've been talking a lot about exponential functions. Today we take that to graphing exponential functions, and we're going to discuss in detail different aspects of exponential functions. So let's just go ahead and get started. At this point, you've got some things that you need to fill in your notes. So the standard form of the exponential equation or the exponential function, as we talked about yesterday, is y equals a times b to the x power, where a is the initial value or the y-intercept. You need to fill that in as well. And b is the multiplication or multiply factor. Sometimes it's called the multiply number, or sometimes it's referred to as the growth factor. And this slide is sort of putting together all the things that we've been going through in the last couple of lessons. Yesterday we realized that when b is greater than 0, or excuse me, greater than 1, and we've got some more things we need to fill in here, that tells us that we're going to have an exponential function that is increasing, and as we learned 2 lessons ago, that also can be thought of as exponential growth. And a generic graph of an exponential function that is increasing or represents exponential growth would look something like that. So make sure you have everything inside of that rectangle written down in your notes. We also, yesterday, talked about the fact that when b, or the base, is in between 0 and 1, that this leads to an exponential function that is decreasing. And a couple of lessons ago, we referred to that as exponential decay. And the generic graph of a decreasing exponential function typically looks something like this. So I'm going to stop so that everybody get caught up on everything on this slide. So this sort of summarizes everything we've been dealing with in the last couple of lessons. But today our focus is going to be on graphing exponential functions and then finding specific things from either the function itself or from the graph. So number 1, and you'll notice in the notes today I've left off some stuff, so you're going to have to fill in some things, and I kind of hinted that I was going to start doing that in the notes for the remainder of the year. So go ahead and write down the equation for number 1. And what we want to do is we want to graph that. Well, we can think of this, if we want to link this back to what we talked about yesterday, as 1 times 2 to the x power. And the reason why we can do that is 1 times anything is whatever you're multiplying by. 1 doesn't change the value of what you're multiplying by. And so what we're going to do here is we're going to set up a table, and we're going to use for the x values, which earlier in the year we referred to them as the domain values or maybe the input values. We're going to use from -2 to +4. All right, so let's kind of get this table started here. When x is -2, the y value would come from 2 to the -2 power. And of course, 2 to the -2 power is 0.25 or 1/4. And I'm going to let you finish that table. All right, so let's start plotting these ordered pairs. So our first ordered pair is -2, 1/4. So on our coordinate plane, it would be approximately right there. When x is -1, we have 2 to the -1 power. That gives us a value of 1/2. So plotting our -1, 1/2, excuse me, that would be approximately right there. When x is 0, we have 2 to the 0 power, and that, of course, leads us to 1. And that is a very important value right there, 0, 1. So I'm going to use a different colored dot for that. That, of course, is the initial value or the y-intercept. 2 to the first is 2. Plot 1, 2. 2 to the second is 4. 2, 4. Plot that. 2 to the third is 8. 3, 8 is plotted right there. And then when x is 4, we have 2 to the 4th, which is 16. So we have an order pair that's 4, comma 16. And then when we connect those together, that's what the graph of y equals 2 to the x power should look like. Now, before we go on here, once again, this value right here is very important. This is the y-intercept, or the initial value. But one other thing here, and that's one of the reasons why I had you rewrite the exponential function like that. That 1 represents the initial value. What does this 2 right here represent? So once again, the 2 represents the multiply factor or multiplication factor, or however we want to think about that. So what in the world does that mean? Well, what that means, as we go up in values of our inputs, the y values are 2 times bigger. In other words, if we multiply 1/4 times 2, we get 1/2. If we multiply 1/2 times 2, we get 1. If we multiply 1 by 2, we get 2. If we multiply 2 by 2, we get 4, and so on. That's what the multiplication factor gives us. And sometimes when we're creating our table, if we utilize that strategy, we can save some time, okay? But before we get to another graph here, we're going to answer some questions from that graph. And since I don't have any more room on that screen, I've got to wipe all that stuff off except the equation. So I want you to answer all 4 of these questions. Notice that in your notes, the first coordinate plane is number 1 and the second coordinate plane is number 3. This is the reason why. It's because after every graph, the next numbered problem, I'm asking you some questions based on that graph. All right, let's take a look at all 4 of those. We already talked about the initial value for that one. The initial value is 1. If we think of it as the y-intercept, that's 0, 1. We already talked about the fact that the multiplication factor, or the multiplying factor, is 2. Is the rate of change for this one increasing, decreasing, or constant? It's increasing. Is this growth or decay? This is growth. All right, very good. Let's now go to number 3. Write that exponential function down. Y equals 10 times 4/5 to the x power. Now sometimes when we're graphing these things, it's easier if we think of the decimal value of that fraction. So when I say to you, we can also think of this as 10, y equals 10 times 0.8 to the x power. Recognize the fact that 4/5 is equivalent to 0.8. It's the decimal value for that. And for calculator purposes, 0.8 is a lot easier to deal with than 4/5 is. Okay? So, like the last one, let's set up our XY charts. Let's use from -2 to 4. I want you to go ahead and find all of the outputs and graph the function. You definitely have to do the 10 times 0.8 to the -2 power, which we just did on the calculator. That's 15.6, right? Now, if the multiplying factor is 0.8, that means each succeeding term gets bigger by 0.8. Or actually, it gets smaller because you're multiplying by a number less than 1. So what's 15.6 times 0.8? Somebody do it. What is it? 12.5? Is that right? Because I know, since these two are right next to each other, that it's going to get bigger by, or smaller by, 0.8. Same thing for the next one. If I take 12.5 and multiply by 0.8, what do you get? Come on, you should know that one without doing anything. You get 10. Now, how should I have known that without doing anything? Because that's the y-intercept. And when x is 0, that gives us the initial value, or the y-intercept. And then 10 times 0.8 is 8. I'm trying to show you a little bit faster way of getting to the next value. And that's the power of knowing two things: the y-intercept and the multiplying factor. Okay? All right, quickly go ahead and finish off that table. All right, let's take a look at the rest of the values. When x is negative 1, we end up with 12.5. When x is 0, we end up with 10. When x is 1, we end up with 8. When x is 2, we end up with 6.4. When x is 3, we end up with 5.1 approximately. And when x is 4, we end up with 4.1 approximately. And of course, we should note, since the b value is between 0 and 1, this has to be a decreasing function, and we can see that it is. All right. Just like in number 2, I want you to answer all 4 of those questions. I'll give you about 45 seconds. Initial value, of course, is 10. If we think of it as the y-intercept, that's 0, 10. The multiplying factor is either 4/5 or 0.8. This is a decreasing function which represents decay. All right, let's go to number 5. Okay. When x is negative 2, that's 138.9. If you're going to multiply by the multiplying factor way, you could just take that and multiply by 0.6 to get to the next value, or you could do 0.6 to the negative 1 power and then multiply by 50, and so on. As I'm going through these, any questions about that table? Yes? All right, and then our graph looks like this, and I'm not going to make you answer those 4 questions again. It is obvious in this one that the initial value is 50 or 0, 50. The multiplying factor is 0.6. It is decreasing, and that represents decay. All right, let's go to number 7. Try that one. So once again, this is not an exponential function because the x is not an exponent. It's just y equals 1/2 x, which is linear. So we know our y-intercept is 0. And rise 1, run 2, rise 1, run 2. This is linear. It's a straight line. So now if we tried to answer those 4 questions, what's the initial value? 0. It is 0. Good. What's the multiplying factor? No, it's not.
Or it's x.
No.
It's 0, 1,
There isn't one. When you have a linear function, back from Unit 2, we were adding on the same number. So this is what would be called the adding factor or the addition factor, not the multiplying factor. As far as the rate of change goes, and this links up to what we talked about yesterday, is it increasing, decreasing, or constant? It's constant. That's the difference between linear and exponential. Exponential is either increasing or decreasing, but linear, they always have a constant rate of change. And it has neither growth nor decay because it's a constant. The rate of change is constant. All right, I have another graph here, but I don't think that we need to do it. I just want to make one point here, and that's the fact that if we do have some sort of fraction, whether it's proper or improper, probably easier for you if you're asked to graph it to convert that to a decimal and deal with it that way, okay? All right, so let me just go ahead and zip through this one. We're going to end today with 4 problems where I'm not making you graph. I'm only going to give you the function, and you have to answer those same questions that I asked you on the other ones. I think I hit the back arrow by accident here. Here, I'll give you the equation for number 11 while I'm going through this. 11 is y equals, so write this down, y equals 10 times 1.04 to the x power. And there it is. There's 11 and 12. Go ahead and answer 11 and 12. Number 11, the initial value is 10, or 0, 10 as the y-intercept. The multiplying factor is 1.04. That is increasing because b is greater than 1, and that represents exponential growth. Number 12, the initial value is 12, or 0, 12 as the y-intercept. Multiplying factor is 0.97. Since that's between 0 and 1, it's decreasing, which represents exponential decay. Last two problems for today. Go ahead and do the same thing with those two. 13. Initial value is 2, or 0, 2. Multiplying factor is 5/4. That is an increasing function that represents exponential growth. Number 14. The initial value, that is linear, remember, but it still has an initial value or a y-intercept of -4 or 0, -4. There is not a multiplying factor because it's linear. The function is constant, and it is neither growth nor decay. All right, we are